Mr. Amit Kumar sir. We are honored to welcome Mr. Amit Kumar Srivastava, a Fujitsu Fellow and a Global Distinguished Engineer who leads AI and technical innovation initiatives at the Fujitsu. Renowned for his technical leadership and expertise, he has made significant contribution in developing AI strategies, advanced solutions, and mentoring global teams. Mr. Srivastava is also a recognized thought leader, frequently sharing his insights on the platforms such as the Times of India. He has been an eminent speaker at the prestigious forum, including MachineCon CGC Summit 2025, reflecting his impactful presence in the AI ML community. His work highlights strong technical excellence, AI governance, and innovations at a global scale, inspiring professionals and the students alike. Uh, Thank you, sir. Welcome. Uh, I would like to hand over you.
Sure, Professor. I'm just trying to find from where I can unmute myself. Okay, it's muted already. Well, when you are into the presentation, you'll not be able to see that Zoom features. Okay. Also, I will not be able to monitor the chat because I'm in the presentation mode, but maybe I can take questions after the session or
Well, if
maybe in
any
between.
participant put the question, then I will inform
Yes,
you, sir.
yes, yes. Yeah, because when I am presenting, I will not be able to see the chat or monitor the chat.
Yes,
Okay,
sir, sure.
that would be helpful. Okay, okay. So first of all, good afternoon to all of you, and thank you for inviting me as part of this faculty development program. So over the next hour or so, we will be exploring one of the exciting frontiers in AI. Basically, a shift from system that only predict to system that can actually reason and explain why thing happens. This is what actually I'm going to cover today. And the topic I will be talking you through is Fujitsu Casual AI Framework, enabling intelligent data-driven decision making. This will introduce you on a high level to Fujitsu's recent work on casual knowledge graph. Some of my researchers, like colleagues, have been working on that. That's why I thought to basically put this topic because this is very recent work. And there was press release around it as well. So I thought to basically have this, and this is an interesting topic, and possibly many of you like this as well. So this solution that I'm going to basically discuss today is more on casual knowledge graph and an algorithm called layered lingam, which together form the foundation of Fujitsu Casual AI. We'll discuss about all of this. And to make it relatable, I will be focusing on healthcare use cases, how casual reasoning is being applied to uncover the true factors affecting sleep quality, let's say lifestyle related disease, and even genetic behavior relationship. The aim for today is not to deep dive into the mathematics, because what I understood or what I got to know that we have a diverse, uh, background professors coming from different departments. So I thought not to get into that. But the idea is to help us understand how casual thinking transforms causal thinking, not casual, sorry. Causal thinking transforms healthcare analytics, making AI explainable, reliable, and actionable for doctors, researcher, enterprise, policymaker, and others as well. So let us begin by understanding the world in which our decision now operate. We often describe today's environment with the term VUCA, that stands for volatility, uncertainty, complexity, and ambiguity. It originated in military strategy. I think most of you might be aware about this as well, but it perfectly captures the realities of our social business and research ecosystem. So, volatility refers to how rapidly and unpredictably condition changes. For example, as mentioned here, sudden shift in health trends or market behavior. Similarly, in uncertainty is when outcomes remains unpredictable despite the data that you have, such as emerging diseases or new consumer responses. In complexity, basically it reflects the interconnected nature of modern systems like lifestyle, genetics, and environment all influencing health outcomes. and in ambiguity that arises when cause and effect relationships are unclear. For instance, incomplete medical data or mixed signals in economic policy. Now, in such a world, traditional intuition-based decision making actually no longer suffice. We rely increasingly on data, but the data alone are not enough. The real challenge is integrating diverse sources. Quantitative data, you can also call textual knowledge, also human expertise, and reasoning through them logically. So that's also one of the real challenge. And that reasoning must be grounded in casual causal relationships, not surface level correlations. So when we understand why outcome occur, the true cause effect pathways, we can design more effective interventions and policies. This is the foundation for what Fujitsu or anyone calls intelligent reasoning, the ability of AI system to support human decisions logically and transparently. However, before I get into those, Fujitsu approach, we must recognize a limitation in most AI system today. They are remarkably good at spotting patterns, but poor at understanding why those patterns exist. So let's first understand that part. So in the last slide, we seen that, or we understood that how the world around us is characterized by volatility and complexity. Now, the next question is that why are our current AI system often unable to make dependable decision in such environment? Uh, so before getting into this point itself, let me just put some more inputs from my side. Like, for example, imagine a medical data set showing that people who carry umbrella also have higher rates of cold symptoms. So a correlation-based AI might conclude that carrying umbrellas cause illness, but a causal reasoning system would recognize the real factor, that is rainy weather, which increase both umbrella use and the likelihood of catching a cold. Without this causal understanding, decisions can be misleading or even harmful. Now, if I have to basically discuss this LLM and conventional AI, even in more detail, let's for an example, because these days people are talking about LLMs as well. So I thought, why not put this as well? Because some of our works were around this as well. So most of the today's AI system, including large language models, performs exceptionally well at recognizing pattern in large data sets. We all have experienced it. They can detect associations and trends across millions of data points with high accuracy. But these models are fundamentally built on correlations, not causal relationships. They can predict what might happen but cannot explain why it happens. For example, they may identify that two variables move together, but not whether one truly influenced the other. So that's also something, one of the limitations that we basically think of. And when such correlation-based systems are applied to real-world or domain-specific data, their conclusions can be fragile or biased. In healthcare or policy, where many interrelated factors exist, this can lead to misleading outcomes or incorrect decisions. Now, this is one of the factor, or maybe therefore, causal reasoning becomes essential. It helps identify true cause and effect relationships and enables reliable logical decision making, something that correlation alone can never guarantee. So correlation is not equal to causation. So having seen where conventional AI stops short, our next step is to explore how we can move beyond correlation towards understanding why things happen. In the next slide, I'm going to discuss, or I'm just now discussing the fusion part. When I say fusion, this is more from a Fujitsu perspective where this knowledge graph and causal analysis actually got integrated or combined together to create something unique. So basically, this is to overcome the problem that we discussed. we introduced a framework that combines these two powerful ideas, causal analysis and knowledge graph. If any one of you is not aware about knowledge graph, so please wait for some time. I'm just going to cover in a slide, possibly in the next slide, just to touch base on what is knowledge graph. Now, the fusion concept is basically think of causal analysis as the engine that uncovers why something happens, the true cause and effect links hidden in data. And think of a knowledge graph as the structure that captures what we already know, like entities, relationships, and context drawn from documents or expert knowledge, or maybe from some prior research. Now, when these two are fused, we get a system that not only connects facts, but also understands their logical relationship. For an example, in healthcare, a standard AI model might learn that exercise and lower blood pressure are correlated. But a causal knowledge graph goes deeper. It can reveal that exercise improves cardiovascular health, which then reduces blood pressure, making the chain of reasoning explicit and explainable. This is how we move from prediction to explanation. And the result of this fusion is a framework that can integrate heterogeneous data source like numerical data or maybe text data, expert role, and reason over them in cause and effect manner. It becomes a foundation of transparent, trustworthy, and explainable AI. Now that we have seen or understand this fusion, the next logical step is to look at what exactly causal analysis means, how it works, and how we mathematically identify cause and effect from raw data. Now, let's understand the first core component, that is causal analysis that we were discussing. This field focuses on identifying why outcome occurs or why outcomes occur rather than simply observing what pattern exists. In traditional data analysis, I think many of us have experienced this. We often stop at finding correlations, like observing that people who sleep less also tends to have higher stress. But correlation alone does not prove which one influenced the other. So that's the problem. But causal analysis attempts to answer the deeper question. Does lack of sleep cause stress or does stress cause lack of sleep? That's something that causal analysis try to answer it or attempts to answer it. Now, using mathematical and statistical technique, causal discovery identifies cause and effect relationship directly from data without needing any prior assumptions. The model tests dependencies among variables and determines which direction the influence likely flows. For example, if changes in exercise consistently precede changes in heart rate, the system infers that exercise may cause the variation in the heart rate. And the output of the analysis is a causal graph, a visual representation showing how different factors are linked through cause and effect. Each node represents a variable for an example, such as diet, sleep, age, or whatever you want to add. And each arrow shows the direction of influence between them. So this causal graph becomes the foundation for explainable AI reasoning. So the right side that you are seeing here, you have some data, tabular data, and then you applied statistical causal discovery, and then this is how the output looks like in form of causal graph. Now, let us look at the three main approaches the researchers and industry use to uncover cause and effect relationship directly from data. The first one is constraint-based approach. This method identifies causal links by performing conditional independence tests between variables. The idea is simple. Let's say if a variable A and variable C are independent. When you control for variable B, then B might be causal intermediary between them. The PC algorithm that is mentioned here as an example algorithm, named after its inventors Peter and Clark, it's a classic example. It builds a causal graph step by step by removing links that do not hold up under these independence tests. These methods are mathematically elegant but can become computationally very expensive for large data set. So again, although we have such algorithm, but there are a lot of challenges that people face using these kind of algorithms. Now the second approach is score-based approach, and this score-based family takes a slightly different route. Instead of testing independence, it searches for the graph structure that best fits the observed data. Based on scoring function like likelihood or Bayesian information. For an example, the GES algorithm or greedy equivalence search algorithm is a typical example. It tries different causal graph candidate, scores each and keep the one that is the best. That best explain the data basically. And these methods are powerful when the search space is manageable, but can be sensitive to noisy data or limited samples. Again, in real world, you will always find that kind of noisy data or such kind of data. So again, there is a challenge. Now the other one is function-based approach. And this is possible in this category. Specifically, it's the most advanced category of the approach in this list, which explicitly models how cause produces effect through mathematical equation. Here we learn functional relationship directly, not just connections. The direct Lingam algorithm, the one that you are seeing it here, it's a well-known algorithm or and well-known example based on linear non-Gaussian model. And what Fujitsu has done, Fujitsu has actually extended this with its IP, like a proprietary algorithm called layered Lingam, which significantly improves speed and accuracy. In fact, layered Lingam can perform causal estimation roughly 1,000 times faster than conventional techniques while maintaining the interpretability, making it suitable for large-scale real-world application. Now, the key takeaway from this particular slide is all these three approaches share the same goal: to identify true causal structure in data. The difference lies in how they search for and validate these structure through constraint scores or functions. Fujitsu builds upon these foundations to make causal discovery both scalable and practical. Now, with these methods in mind, let us now see how causal discovery connects with knowledge graph, giving structure and meaning to the relationship we are going to uncover. That's what we explore in the next slide now. Now, this slide actually marks an important transition because it connects the statistical side of causal discovery with the structural intelligence of knowledge graph. Now, if you see, causal discovery is about uncovering why outcome occur. It finds the real cause and effect links hidden inside the data, the logical pathways that explain what we observe. Now, in real world setting like healthcare, as we are discussing, things are rarely simple, as we all know or have experienced as well. Like lifestyle, genetics, possibly an environment all interact. Such interconnected variables make it hard to see what truly drives an outcome. So really challenging. That's where knowledge graphs come in. They organize what we already know, entities, relationship, and context, creating a network of meaning across diverse data sources. Now, when we combine causal discovery with a knowledge graph, we get a system that links the why with the what. It connects discovered causes with established domain knowledge, leading to reasoning that is both connected and explainable. So, this is the flow that you can basically imagine for now, that we start from raw data and then basically we apply causal discovery to uncover relationship. We enrich this with knowledge graph and then finally arrive at causal knowledge graph, a unified framework that represents both facts and their causal logic. So we have to basically reach at causal knowledge graph. Now, in short, causal discovery gives us the reasoning, and the knowledge graph gives us the structure. And when you put them together, they form the backbone of explainable human trustworthy AI. So now let's see the basic of knowledge graph, because many of, or maybe few of you might not be aware about knowledge graph if not from computer science or possibly AI domain. Uh, so I just put a simple slide here so that I can quickly go through it. Uh, if you see this, knowledge graph models reality as nodes and edges. So there is a node and there is an edge. Uh, each node represents an entity, and entity could be like, let's say a person, maybe a symptom, a machine, whatever. And each edge defines the relationship between them, such as causes, belongs to, or interacts with. In short, it's a digital mirror of how information is connected in the real world, the one that you are seeing at right. These are nodes, and this is the edge, and this is how it is connected. X is a part of Y, something like that. Okay. Now, because everything is linked, a knowledge graph can merge data from multiple sources. So one of the good factor, like you can have a data from, let's say, databases, documents, or maybe sensors into a single unified structure. And this removes silos and allows consistent reasoning across diverse information. And unlike traditional databases that store flat tables, knowledge graph easily handle many-to-many and hierarchical relationships, even cycles like feedback loops in biological or industrial system. And this flexibility makes them ideal for modeling complexity. Once the information is connected, we can perform both deductive reasoning, that is drawing logical conclusions from known facts, and the inductive reasoning, that is discovering new patterns from the structure itself. This means the system can answer not only what is related to what, but also what might logically follow. So in essence, if you see knowledge graph, it provides context and connectivity, while causal discovery provides direction and explanation. And when you combine these together, they can enable AI system that can think, infer, and reason much like humans do. On the next slide, let's see why causal reasoning becomes critical even when we have, already have such rich connections. So more from the motivation side of why we are looking at this causal reasoning. So we have seen knowledge graph, what knowledge graph can do in very brief, and that it connects data meaningfully. The next question that we have to ask from ourselves, like, why do we still need causal reasoning? So this slide is basically going to explain that. So in most analytics today that we do, we rely on correlations. I think we already have discussed, that is patterns that appear connected. But correlation can be deceptive. Two things can move together without one causing the other. For example, cells, ice cream cells, right? And drowning incident both rise in summer. But ice cream does not cause drowning. The real cause is temperature, right? And similarly, in business and policy side, you can also have similar misleading correlation, and that can lead to wrong strategies. Now, this is where causal reasoning makes a difference. When we understand why something happens, the actual cause-effect relationship, that is, our decision becomes logical, transparent, and defensible. For instance, instead of merely predicting that employee turnover will increase, causal reasoning help identify what specific factor drives it, like perhaps workload, leadership quality, or career related issues. Now, the point is, uh, I would say, therefore, causal relationship becomes the foundation for data-driven management. It transforms data from something we react to into something we can reason through. And it also enables organization to not only forecast outcome, but also intervene intelligently. That is, to choose actions that can change those outcomes in desired ways. I can go through this example, like this picture, for an example. If a correlation is found between the number of Nobel laureates, like that you are seeing it here, and chocolate consumption, it would be meaningless to implement a policy of distributing free chocolates to employee with the aim of producing Nobel laureates from within the company based on the results, right? So uh, that's why that causal reasoning actually is very important. Now, let's understand the limitations here, or the challenge for it. Why traditional approaches alone are not enough, and how these kind of new innovations address them. Even though causal reasoning is powerful, as we have understood, traditional causal methods come with their own challenge. And this is what I'm going to discuss in this slide briefly. Now, the first limitation is that many existing causal models are qualitative, not quantitative. So that's again one problem. They actually capture cause and effect relationship in terms in let's say in text or diagram, such as you can say AI influences B, but does not tell us by how much or under what condition. So that's one problem. And without measurable strength or direction, these causal links cannot drive reliable predictions or decision model. Now the other one is bias in estimation. It's a purely data-driven method, can sometimes invert the direction of causality, especially when confounding variable exists. For example, if I take an example, let's say in a data set where medication use and recovery are linked, the model might incorrectly infer that recovery causes medication, but an inversion caused by unobserved factors or sample bias. So it might happen, right? Now, the another challenge or limitation in this method, or in casual methods like that is a traditional casual method we are talking about, uh, is basically data is often fragmented across domains. For example, healthcare, lifestyle, environment, or genetics. So they are fragmented, and each domain may reveal particular causal insight, but without integration, we miss cross-domain relationship. And this fragmentation limits our ability to form a complex or maybe a complete causal view of complex system. So that's again one of the challenge or limitation that we face in the real world. Now, in summary, if I have to basically summarize this slide, uh, traditional causal methods either lack quantification or suffer from bias or fail to connect across data set. Now, overcoming these limitations requires some innovation, or maybe some approach that combines data-driven accuracy with knowledge-based reliability. And this is what I'm going to now talk in the upcoming slide. So, yeah, before actually even going to that, let's understand this traditional data analysis problem. Last, we were basically looking at causal methods like limitation in current causal method that we already have discussed few of the algorithms in the past. And here we are actually going to discuss the data analysis related limitations that is a traditional machine learning that we do. So, and then this is important to understand because we have to define from a different angle or different lens, and it's equally important. We cannot just understand the limitation of causal, but we should also understand like why we basically move to the causal part, but why data analysis was also not sufficient. So that's also important for all of us to understand. So traditional analytics is designed to capture aggregate trend. If I just put it on a very loose term, it's a very good at describing averages, for example, average customer behavior or maybe average treatment outcomes, but it misses the relationship that hold only under specific condition or for particular subgroups. And the result is insight that may look correct overall, but fails when applied to individuals. So it's very important to understand. When it applied to individuals, it may fail. And this is where basically we are moving towards like personalization, like individual causal thing, and not aggregate or a group kind of thing. Now, the second limitation, as I briefly touched, is traditional methods rarely uncover individual level causes. They can tell us that on average, marketing increases sales, but they can't tell us why one customer buys and another does not, even with similar data. Very difficult sometimes. And in healthcare specifically, this translates to knowing population level risk factors, but not why a specific patient responds differently to treatment, possibly the same treatment. Sometimes it happens. Even experienced domain experts can miss rare or unexpected causal patterns because human reasoning is biased towards familiar explanations. And traditional statistical summaries tends to average out these unique variations rather than highlight them. For instance, if you see in oncology, doctors don't just need to know which genes are common in cancer patients. They also need to identify the unique gene expression that explain why this patient cancer behaves differently. And traditionally, or maybe traditional analytics cannot isolate such individualized insights because it is correlation based, not causal. In fact, just to add, like we had worked on similar solution even with the old causal techniques, but today I'm not basically discussing the old techniques that we have covered. I'm just covering the recent one that Fujitsu Research has worked on. Now, the implication is basically this limits extends beyond healthcare. This limitations actually extends beyond healthcare. It affects also marketing, manufacturing, and finance as well. So you can utilize such kind of think or basically understand from those domain perspective as well, and not only limiting to the healthcare. And I think we all have experienced such kind of activity. Those who are into the data science kind of domain or statistics kind of domain, they must have experienced such issue. And now this is what I was talking about. The next frontier is moving from population level correlation to individual level causal reasoning. And this shifts allows system to adapt to people, not averages. So while traditional data analytics describes what's happening in general, causal reasoning explains why it happens in specific cases. And now in the next slide, I'm just going to discuss some of the techniques or maybe what Fujitsu was basically doing to overcome this challenge or maybe specific areas. Now, I think we discussed about this qualitative understanding only, data bias and inversion and fragmented data set. These were the challenges we discussed. And these were the traditional causal methods and, they had these three major challenges. Now, this slide actually going to explain how Fujitsu has significantly overcome each of these barriers. So the first one that you are seeing is basically related to the qualitative understanding only, and there was no quantitative as we discussed three challenges before as well. What we have done or what Fujitsu has done, because Fujitsu has addressed this by integrating causal knowledge extracted from documents and expert literature with quantitative data-driven discovery. Will basically go through the architecture as well, like high-level architecture in the upcoming slide. So if this is not making much sense, that is perfectly fine. In the next slide or subsequent slide, you will be able to understand what I'm talking about. So basically, this hybrid approach allows AI to reason across both text-based and numeric evidence, producing measurable causal insight, not just descriptive ones. So the outcome was enable measurable causal insight that was missing in the traditional causal related algorithm. Now, the second one is related to data bias and inversion. This is where basically we introduce layered lingam innovation, uh, the architecture actually. So it actually advanced function-based algorithm that we had seen in the previous slide as well, that improves both speed and reliability. Now, compared to the earlier methods, it achieves nearly 1,000 times faster causal estimation without sacrificing accuracy. So more importantly, it ensures stability and logical consistency in causal direction. So, which is essential for fields like healthcare and finance, very important. Now, if you see the last one, that is fragmented data set, we also try to address this. And how we did it? Basically, we developed cross-domain causal alignment, which allows independent data sets, says, let's say, lifestyle and genetic data, to be connected through shared causal relationship. And this result in a holistic causal view, helping expert make sense of complex multi-factor problems like disease progression or personalized treatment. This is where basically we are thinking for personalized treatment, individual. And when you bring or when we have bring all this together, then you can call it as a Fujitsu causal knowledge graph, and it combines data-driven causality with expert domain knowledge. In short, Fujitsu has turned causal discovery from a slow academic exercise into a fast, scalable, and explainable technology. Now that we have seen this, let's further explore this causal knowledge graph and what it actually contains. That will be important for all of us to understand. Now, these are the contents of causal knowledge graph we are going to basically discuss. I will just spend possibly maybe 5 minutes on this slide. I will just take some time so that the subsequent slide will be very easy to understand. As I mentioned earlier, I am not getting into the mathematics or not discussing the cost function or whatever we are optimizing. But again, if you want to try this kind of solution, you can always go to Fujitsu Research website and basically create your login there. And possibly there might be a trial version. I need to check, but there might be a trial version to test it. Now, if you see in this particular figure, A, that is basic form, uh, since this kg, that is knowledge graph, and I say kg, you just understand it's knowledge graph, short form. The basic unit is a triple consisting of two nodes, that is in ellipsis, like event x and event y, and connected by a single row arrow. And the nodes represents events, with the event at the base of the arrow being the cause and the event at the tip of the arrow being the effect that you are seeing. Okay, the base and the tip, cause and effect. Now, therefore, this particular solid line, if you see in between, that is the H, represents event X causes event Y, that is cause and effect. This is a causal relationship, which is the basis form, which is the basic form. Now, the dotted lines that you are seeing here, the dotted line that you are seeing it here, it represents an optional additional information. So, an example where causal effect is added. Since causal effects are usually represented numerically, they are shown as string types in the square box, okay, rather than entity type ellipsis. Now, if you see figure B, this one, it's an example where meta information is added. You can add name, like let's say graph name. For example, whatever graph name you want to add, okay, just to show. Right? Because in C we are going to say it as a graph one, so that's why I'm saying you can add any graph name or graph name here, and basically, or possibly what you can say, like here meta information indicates that graph one was created from document one. If you see from this particular picture, this graph one, that's why I was saying you can just have this graph named from your side. Just think it is a graph one, okay. Um, Now, if you see this meta information part, it actually includes information about the data source or the program used to create the causal relationship. Additionally, if it is a numerical data, you can include conditions at the time of observation also, or statistical values such as mean and variance. See from if you see into this perspective. Now, in the example, this image C, it's an example where causal relationships are overlaid. Here, the meta information indicates that graph one, this one, was created from document one, okay, using a causal extraction program. And it shows that two causal relationships were extracted. Event A causes event B effect. this one. If you see event A causes event B has been fed. Similarly, for graph 2, it indicates that graph 2 was created from data 2 using a statistical causal discovery program, this particular graph 2. And then again, you can just interpret the cause and effect like this based on the arrow that, that we are seeing it here. So again, and then when you go to this D figure, it's an example where additional information other than causal effect is attached to the causal relationship themselves as an option. And this allows for description of mediators or side effects that occur when a certain causal relationship takes place. Now, if I have to, or if you have to understand this in very high level, I would say. So this summarize or this figure summarize how Fujitsu causal knowledge graph brings together events, evidence, metadata, and quantitative causal effects into one unified representation. And it actually enables both transparency and explainability. I'm going to discuss about all of these components in detail, like how in the enterprise it actually looks like in a very high level. So even if it is not completely understood, that is perfectly fine. Then possibly in the next slide or upcoming slide, we'll dive into this into more easy to understand way. Now, this is how the system structure of causal knowledge graph related technology looks like. This is basically this shows how all the related technologies come together to form Fujitsu causal knowledge graph system. It integrates both document-based causal knowledge and the data-driven causal estimation into single framework. Now, if you see from here, first, known causal relationships are extracted automatically from scientific and technical documents and stored in a graph database, any graph database, okay? And then these becomes the system's prior knowledge, what we already know from expert source. Similarly, in this statistical causal discovery from data phase, uh, it's basically for numerical data set, unknown causal relationship are discovered statistically using method like, Fujitsu has created like layered link method. These new causal links are also stored in the same graph database, the one that you are seeing it here only. Now, when multiple data set exist, like there could be multiple data set, there. For an example, from different studies or time periods, the system performs integrated causal discovery. That's why you are seeing this word integrated causal discovery. It combines their conditions and statistical features like means and variance to infer cross-domain causal links. Now, finally, both the document derived and the data-driven causal links are unified at the event level. So it means that the same event appearing in both sources is merged into a single entity. This creates a complete causal knowledge graph. This is what it is creating, complete causal knowledge creation, knowledge graph. It's an integrated representation that merges expert knowledge and statistical evidence. Now, once constructed, this graph is continuously used in two ways, both as a knowledge base for future discovery and as a foundation for practical applications that we'll be going to see possibly in next few slides. It's a self-reinforcing system. Each new discovery strengthens the knowledge graph, and the graph in turn improves further discoveries. So this is how actually the system structure looks like in a very high level. And connecting to all this technology actually provides such kind of powerful, methods. Now, let's understand a little bit more on the layered lingam algorithm. I'm just checking the time. Just a minute. Okay, we have time. So now this slides highlights one of the Fujitsu key research as we discussed, like layered lingam, presented at ECML PKDD 2024. It builds on the traditional lingam framework, but introduce a layer structure that makes causal discovery dramatically faster and scalable. Like we discussed about 1,000 times faster, but how? So this is one of the reason, like through this particular technique or the work that we had done. So on the left side, you can see the baseline, that is direct lingam. And it's a a traditional causal algorithm. So it estimates causal order among variables one at a time, which creates a major computational bottleneck. As the number of variables increases, deciding the exact sequence becomes exponentially slower. And the middle one that you are seeing, this layered linker, the Fujitsu work, it solves this by introducing the concept of layered causal order. You can just monitor it here, how these x's are put here and how these x's are basically put here. So instead of enforcing a strict one by one order, the algorithm statistically groups variable that cannot be ordered uniquely into layers and analyze them in parallel. This simplifies this simple but elegant idea, eliminates redundant ordering decision and reduces overall computational complexity. Now, now this is just a graph for performance. Just to put it here. The red line that you are seeing it here is for the layered one, and it consistently outperforms both direct lingam and Rooks-1 method. Both were traditional causal methods. And in experiments on synthetic graph with up to 500 variables, the method achieved 25-fold speeds ups on the average, and in large scale scenarios, nearly 1,000 times faster estimation, all without any loss in accuracy. So what once took hours or even days in causal estimation can now be done in minutes. And this speed and stability makes causal reasoning practical for real world data, because we talk about cause and effect and etc. But if you try it on the real world, it's very difficult sometimes because the algorithms were not equipped from that perspective, or maybe not that powerful to cut down the time or computational complexity, etc. etc. You can do genomic analysis and healthcare to manufacturing and customer behavior modeling, etc. So this layered lingam can transform causal discovery from a research algorithm into an enterprise-ready capability. And in fact, this solution is also available on Fujitsu Kojichi platform. That's a Fujitsu AI research platform, just to let you know. Now that we understand how this causal system discovers and validates cause-effect relationship, this slide is basically showing how those insights are actually used for decision making. So the goal is to provide a recommendation or recommend actions that are effective for the target outcome while keeping any negative effects on the attributes as small as possible. And this process is called optimal causal decision making. And it controls the effect of one action on all other attributes by analyzing multiple causal graphs and finding the best balance between benefit and risk. Now we applied a mathematical optimization, nothing but a linear programming, based on causal relationship, and the constraint ensures that the target variables reaches the desired value. For example, keeping employee turnover below 50%. This is just an example, and then importantly, this condition is verified across all causal graphs. So the recommendation is stable even if the data context changes. It's very important. Now, the objective function, basically, I have not mentioned the mathematical formula here, but just let me just speak in a very rough way. The action cost is the effort or investment required to take that measure, and the change in causal effects on other, that is non-target attributes, meaning it tries to avoid causing harm elsewhere in the system. So these are the two objective functions, minimizing these two things. Basically, if I just speak it roughly, in a English language, not mathematically. Now, the conventional approach, the graph or the image that you are seeing it here, sorry, it's in Japanese and also very small, so possibly you might not be able to see what it is written here, but you can understand this arrow sign, right? So I think this sign is positive and this one is negative. So I think you can relate from that perspective. So the conventional approach actually achieves the main target, but unintentionally creates several negative impact shown by something called, I would say, the red color or whatever color. I'm not very sure which color is this, but this is shown by this particular color. And in contrast, if you see the Fujitsu causal optimization, that is in this particular color, it achieves the same target while minimizing negative impacts on other metrics as highlighted in the this particular red box. They are all into the positive direction and not like this, right? Now, this approach moves beyond predictive analytics. Instead of only predicting outcomes, the system now provides recommendation or recommends the optimal actions that achieve desired results efficiently and responsibly. Uh, Now, it also brings explainability and control into decision making, allowing organizations to choose interventions that are both effective and safe. Now, again, this is one of important concept as well. I think when I am discussing about this optimal causal decision or high-speed causal discovery, this is nothing but these things we are discussing: statistical causal discovery from data, integrated causal discovery, and then causal decision making, causal knowledge transfer. This is what actually we are discussing, in these slides. Okay, so in this one. This is also one of the capability in that Fujitsu's causal knowledge graph architecture, and it's called integrated causal discovery that we had seen in a very high level in the system architecture, high level system architecture that we had seen. This technique enables us to build a single unified causal model by combining data from multiple domains, even when each dataset contains only part of the information. And now the goal is basically to recover a single cause and effect structure from several data sets that have some overlapping variables, but also many different ones. I think you are able to possibly will be able to relate it very easily here, how this data set A, B, C, when basically it moved into that integrated causal model, how some of these actually, you know, some of them actually overlap, like X3 or X5 acts as a bridge that let the system statistically align and merge the database. So this is what actually you are seeing it here. If you see this X3 or X5, basically these overlaps, like X3 and X5 acts as a bridge that lets the system statistically align and merge this data set. This is what we are discussing. So we had to merge this data set. We had to integrate this data set for this causal model, and this is how basically it gets merged. Now, using those overlapping variables, Fujitsu algorithm performs cross-domain causal estimation and builds an integrated causal graph, the one that you are showing it here in this figure on a very high level. Each arrow represents a cause-effect relationship, as we already had seen in past, like knowledge graph and etc. etc. So just to be uh, wanted just to basically relate with that, and the numbers indicates the causal influence, strength or direction, positive or negative or whatever. So what this means is that we can now analyze relationships that span across departments or data silos. For example, combining patient health data with lifestyle surveys or linking employee engagement data with business outcome. And normally such cross-sectional causal analysis would be extremely difficult, but this approach makes it possible. So integrated causal discovery let us move beyond isolated dataset and uncover system level causality. Now, this is the another component that we had seen in the high level system architecture. And here, basically, it's more on the reliability enhancement through causal knowledge transfer. And this approach improves the accuracy and stability of causal discovery by incorporating reliable prior knowledge from existing causal graphs. Now, the main idea is to reuse past causal graphs as prerequisites knowledge when analyzing new dataset. Instead of starting from scratch each time, the system transfers already validated causal relationship and use them to guide new causal estimation. So it's also very important. Why you want to basically do you know uh, every time from scratch if you can learn it from the past causal graphs or past data from that perspective. And the one that you are seeing it here below is actually Fujitsu collaborated with Hirosaki University COI program, which has large scale health data, including lifestyle, diet, exercise information, and the causal graph estimated from this data set shown that you are seeing it here acts as reliability data or prior causal knowledge, this one. basically. Sorry, again, in Japanese. So these were actually data that we basically had as an expert knowledge data or a prior causal knowledge with us. And if you see the right side of the work, basically when analyzing a new data set like customer health or behavior data, the system brings in this prior causal structure to guide the discovery process. So without such knowledge, it's very difficult, or the one that you were saying as a false hypothesis. The algorithm might incorrectly assume every factor directly influence all others, and that's not true, right? In the real world, or possibly even in the synthetic world that you try to create some data for you, it's also not possible there, unless you are, creating that kind of data set from your own side for some purpose. But when we use these kind of prior knowledge, as shown in this reasonable hypothesis, the below one, the structure becomes hierarchical and logical consistent, accurately reflecting cause and effect. Now, the transfer of causal knowledge helps the system maintain consistency across different observation conditions and domains. It allows the AI to generalize what it has learned from one dataset and apply it meaningfully to other. Again, medical example, from medical data to lifestyle data, or maybe from you can also pick another domain as well. I'm not focusing on another domain because today is more around healthcare side, and this work is very important into the healthcare domain because with the organization that we have collaborated, they are operating in the healthcare. We got the data from the healthcare side itself, and we've shown results based on the healthcare. We've shown our algorithm efficiency on the healthcare data set itself. So the intention is basically, or the intention was to create that. But it's a fundamental or it's a very strong algorithm or method that can be utilized to solve problems in other domains as well, where you need causal kind of thing. But yeah, medical is something that we focused and we tried and we basically solved with some of our partners. So I'm just trying to use the word from the medical domain, and in fact today's session is also around that, so it's very relatable. Now, so this capability enhances reliability by ensuring that every new causal discovery aligns with what is already known to be true. Together with high speed and integrated discovery, it forms a robust foundation for trustworthy causal reasoning. Now, I'm just going to discuss one or two quick case study that was done already. So, based on the techniques or technology we have discussed till now, uh, this case study demonstrates how Fujitsu's causal knowledge transfer capability was applied to real-world health data, focusing on relationship between sleep quality and lifestyle factors. And the objective was to identify true causal factors that influence sleep, not just correlation. When you see most of the studies on sleep rely on statistical correlation, for an example, they say, or maybe saying that exercise or diet might relate to sleep quality. But correlation does not imply causation, we have seen already. Here, the goal was to discover which variable actually cause changes in sleep quality and duration. Again, this seems to be a very simple problem, but when you get a lot of variables, data sources, different data sources, and if you want to basically do a causal thing, it's not that straightforward. Even as we discussed, the traditional causal method will be extremely slow and may not be, provide the exact information we are looking for based on whatever we have seen till now. So for this work, two data sets were actually used as a pilot. One is basically the Hirosaki University COI Next Health Examination data, which includes lifestyle, diet, and activity data from large-scale health checkups. And the second data is basically a sleep health and lifestyle data set collected for this study. The idea was to use the reliable causal graph from Hirosaki data as a knowledge base and apply it to the new sleep data set. Now, this method combines Fujitsu's causal knowledge transfer with Kyoto University's Bayesian network model. So this allowed causal structure from trusted data to guide the learning on smaller, newer dataset, improving both precision and reliability. Again, these are just text and very straightforward, so I'm not, going one by one. I'm just, speaking randomly, but yeah, related topic only. Yeah. Now, if you see the result side, the significance of it, or maybe the result side of it, variables like age or gender and number of steps were found to be true exogenous factors, like meaning they act as cause but not effects. And relationships such as insomnia leading to poor sleep quality were confirmed as causal, not merely correlated. And that's also true, right? And importantly, the system eliminated false causal assumption, such as wrongly inferring that age directly affects sleep duration. I think in possibly two or three slides before, we have also discussed about this false causal illumination, false causal assumption, how actually it basically gets corrected with the new techniques that we have used. Fujitsu basically done that. So just this is the same thing that I'm talking about. Now, this case validated the causal knowledge transfer can maintain reliability even with smaller or diverse dataset. It also highlighted how such causal reasoning can become a foundation for medical and behavioral AI applications, like predicting which lifestyle interventions can truly improve sleep quality. So, through this example, what I wanted to discuss, like how causal AI moves beyond pattern recognition. It actually helps uncover the why behind human health and behavior. Now, if you see this figure, again, this is estimating causal relationship using only the open data on sleep and lifestyle. And this data is basically when estimating causal relationship in the available data using that Hirosaki Health Checkup causal network as prior knowledge. So what we are basically, or what I'm saying it here, in this figure number two, this one, if you just compare it from, I know that is very difficult because these are two big figures, like complex. So, but let's understand this particular figure. Uh, if you see it here, this structure basically is more interpretable and medically valid compared to figure number one. Uh, I will just put some point, you will be able to understand it. So you can see the age, gender, and daily steps. So if you see it here, age, gender, and daily steps appear as true exogenous factors. Okay, but if you see here, it's only insomnia, right? Now here, if you see, these are exogenous factors, age, gender, and daily steps, meaning they are not, or they are root cause without parent node. This aligns with real world understanding. These variables influence other factors but are not themselves influenced. The causal flow shown here in purple that you are seeing it here is also much more logical. A relationship such as insomnia and sleep duration, sleep quality reflect established medical pattern. So if you see it here, and then sleep duration, similar to that, you have sleep quality, quality of sleep, you know, they are now reflecting established medical patterns, that is, poor sleep quality stems from insomnia and shorter duration, not the other way around. If you see in the last one, you know, very difficult. There is no much information from that perspective. Now, let me explain the error correction that is in the green arrow. Uh, the correction basically, when I'm talking about, it's the power of integrating prior knowledge. The model no longer confuses correlation with causation, because we discussed about, right, we borrowed or we basically picked some data, right, from Hirosaki University, and basically on top of it some prior causal knowledge got created, and we transferred that causal knowledge, and then we basically created the solution on top of it, or basically we applied our work on top of it. So what I wanted to say, this is a key observation. Basically, I put it here. It was very difficult to put in the same slide, so I just distributed it multiple slide. Uh, So when you combine all these or combine this new data with reliable prior causal graphs, uh, Fujitsu method achieves most trustworthy and interpretable result. This approach actually enhances medical validity and explainability, which are crucial in healthcare AI. Now, in summary, if I say so, this case illustrates how causal knowledge transfer can clean up noisy, misleading relationship and align machine inferred causality with domain knowledge. This is very important. Now, I will just, have one more case study very quickly, and then possibly we can close it, right? So this is also on recent work that we had done, uh, and this is basically more from a joint research outcome from uh, GeneQuest and Fujitsu, where causal AI was used to analyze how genetics and lifestyle habits interact to influence body mass index, or that is BMI. The focus was to go beyond correlation again and understand the true causal pathways connecting genes, eating patterns, or maybe physical outcomes, etc., etc. Now, the key challenge was to identify causal links between genetic traits such as those affecting carbohydrates or lipid metabolism, or maybe and lifestyle factors like eating and drinking frequency. The goal was to determine how changes in these behaviors could causally alter BMI, not just correlate with it. Now, with Fujitsu's causal knowledge graph technology, that is, as I mentioned, available on Kojuchi AI platform for the trial possibly, the analysis combined genetic data with lifestyle information like eating frequency, food preferences, and beverage consumption. Based on this integration, the system could simulate what if scenario, for example, how modifying eating frequency might lead to an increase or decrease in BMI. Now, the causal graph below here that you are seeing it here shows a relationship among factors such as genes, age, sex, and different food and drinking categories. Again, those numbers plus minus depends on, I'm not getting into that. But yeah, just to be on a very high level, uh, the arrow indicates causal effect direction. We already have seen when we were discussing knowledge graphs and causal, prior slides, and the number represents causal strength. So, for instance, individual with genetic predisposition towards higher weight represents by the Gini node shows a positive causal effect on BMI through food preferences and consumption quality. And now the two findings emerged here, or the two basically insights emerged here. See it here, the below one. The one is genetic susceptibility influence both preferences and BMI, meaning genes may indirectly affect weight by shaping food choices. The second is basically the system could generate personalized recommendation. Very important. Personalized recommendation. This is what we are actually, or everybody in the world is focusing, or maybe in the medicine side. Can we create something very personalized for individuals, such as reducing the frequency of greasy or carbohydrate-rich food, or adjusting portion size to reach a specific BMI target? In this case, let's say from 25.1 to target 22, something like that. Also, this study actually shows or illustrates like how causal AI enables personalized health guidance rooted in both biological and behavioral understanding. It also suggests evidence-based interventions tailored to each individual's genetic and lifestyle profile. Now, this is one basically a cutout from the press release that we had recently. So I just, took this screenshot from press release. Basically, to conclude, I wanted to basically had this slide just to put it very high level. So, Fujitsu causal AI represents a shift from traditional machine learning, which focuses on correlation, to a deeper level of understanding through causal reasoning. This is what we have basically evolved from slide number one till now, right? Now, what makes this powerful is not just the accuracy of the models, but the ability to scale causal discovery across thousands of variables at nearly 1,000 times the conventional speed. And we've seen that, or we understand like how actually it is improving the speed. And equally important is what comes next, that is effective measure planning. This allows researchers and practitioners to design evidence-based interventions where data is not just analyzed but also acted upon, like preventive kind of thing as well. So this actually opens up new possibility where it's health science, economics, education, or maybe behavioral studies, where understanding cause and effect can lead to better decisions. And this is it. Yeah, this is just again one more screenshot where I just put like overwhelming scalability and effective measure planning, etc., etc. And these were some of the references and what credit. Yeah, this is it. Thank you so much for listening to me. And if you have anything to ask, I'm open to that.
Yes, thank you, sir.
Yeah.
Participant, if you have any question, please ask. Please unmute yourself and ask the questions if any.
Or you can also ping me if you.
Sir, I am having one question.
Hmm.
So, how does the error correction improve the biomedical validity of the causal graph?
Sorry, Professor.
How does error correction improve the biomedical validity of the causal graph?
I think in one of the graph, Professor, I shown that negative and positive direction, like
Yes.
how it basically corrects it. So there is a mathematical logic behind it. The one that I was discussing, like linear programming, like to solve that particular constraint and the optimization part. So I think I can share that link with you if you are interested to read it.
Okay.
Yeah, yeah.
Yes.
So it was, put in that slide in a very uh, minimalistic way, just to understand with the arrows, green arrow and that
Yes, yes, sir.
red arrow. Yeah. Yeah.
Any questions, participant? Okay. So, thank you, sir.
Thank you,
I would like
Professor.
to, hello, yes.
No, no, please go ahead, Professor. You were saying something.
Yes, I would like to extend my heartfelt thanks to Mr. Amit Kumar Srivastava for delivering such an insightful and inspiring session. Thank you so much, sir, for sharing your valuable knowledge and expertises with us. It was truly and a pleasure to have you with us today. Thank you,
Thank you,
sir. Thank you so
Professor.
much.
And thank you everyone to listening to me.
Yes,
Thanks.
thank you.
Bye-bye. Bye.
Yes, participant. We will give a 5 minutes break and then we'll again start. Okay. So don't go anywhere. Only take a 5 minute break.
Welcome, sir.
Yes. Good afternoon.
All participants, our guest is now uh, arrived. So we will start our today's session. Um, Dr. Bhushan Garware, he is now our today's guest. We are honored to welcome Dr. Bhushan Garware. He is an AI consultant at the Google, specializing in advanced artificial intelligence and the machine learning applications. He has delivered insightful sessions on the topics like agentic AI and AI agents on the Google Cloud platform and esteemed institutes such as IIM Nagpur and ISACA Pune chapter. Dr. Garware sir, TEDx talk from Gully to Google lessons from the small town dreamer reflects his journey from the humble beginnings to becoming a thought leader in AI. His passion for the teaching and deep expertise in AI maker him a valuable resource for aspiring professionals and students alike. Welcome, sir. I would
Thank
like
you.
to
Thank
hand
you
over,
so much.
sir.
Yeah. Are you able to hear me?
Yes, sir.
Yes, sir.
Yeah. Thank you so much. So let me go to my slides. Okay. Okay, I'm sharing my screen. Just give me thumbs up if you're able to see my screen.
Yes, sir, it's visible.
Okay. So thank you so much for inviting me for this FDP. And I'll be talking about recent advancements of AI in healthcare. I just have one screen. So, if you have any questions, I'll not be able to see your chats or hand raise. Uh, you can stop me and I can answer your query. Otherwise we will have some time in the end of this session, and you can ask other questions.
Yes, sir, no problem.
Okay. So all views expressed in this presentations are my own personal opinions and do not represent my employer's view in any way. Okay. With that, let's get started. So the session is planned in these four sections. We will just have an overview of AI in healthcare. Then I'll be focusing on recent advancements and what challenges that we face. And then in the end, we will wait for Q&A. I have a hard stop at 6, so we have a good 1 hour 30 minutes, and I hope you will enjoy this journey. So let's understand overview of AI in healthcare. So my thought here is, uh, how can we bucketize applications of AI in healthcare? So if you see applications of AI in healthcare, those can be divided into three major categories. Category one is I talked about administrative applications in healthcare. What do you mean by administrative application means? The first comes, and one of the most popular application of AI in healthcare is virtual assistant. There will be so many queries, and there are no human expert to answer all the queries of the patients. If I have a virtual assistant who can take care of the basic queries or very straightforward queries, this is the one that is one of the major application, and it's not restricted only to the answering the medical related queries of the patients, but lot of administrative work like taking appointments, canceling appointments, making the payments, downloading the results, sharing the documents, so many other stuff can be done. Okay. The first application is, and we will go into deep dive, and then we'll discuss about the research opportunities also, like where you can contribute. So the biggest use case is virtual assistant. The next application in administrative talk is called as a note taking and EHR documentation. Now when you go to doctor, in old days they used to write on a prescription and all this happening, right? But how can you maintain the history of the patients and all that? In many cases, Now in India also, you will see that when you're talking to the doctor, the doctors are half the time busy taking the notes on their computer. What has happened, what was given, what were the symptoms, and all that. The question is, now we have amazing AI systems available, and can I free up the doctor from this burden of note taking? When you and doctor, when both of you are talking to each other, can there be an AI system who will understand the conversation between doctor and patient? That is an unstructured data. It's initially you need to go from speech to text, and from that speech to text you need to extract those required entities. And can't you directly put those entries into a database, without, or at least take doctor in a loop, just to confirm everything is correct rather than doing everything? So the second biggest application that I see in administrative side of AI is notes taking. And it is still, doctors are not fully happy with what we have today, but there is a lot of opportunity to build these kind of an applications. The third stuff is about revenue cycle operations. Now, how many of you have this kind of an experience, right? One of your loved one, your friends, they are in a hospital, everything is done, now they're waiting for the claim approval or they're waiting for billing, right? How much time is, spent once the treatment is done, patient is ready to go home, but they are just waiting. Why? The approvals are yet to come, or the billing is not ready, and all that, right? So that's why I call that this is an administrative serve. Come on, do you really need 3-4 hours to complete a simple process, right? Here AI can bring a value, and you will get an amazing experience. You can save, like, imagine 3 to 4 hours per patient. If you are saving, how much is the time saved? Correct. And the next is, data structure, analytics, and interoperability. So now these are the thing, like, there's no monopoly of a one kind of an EHR system, right? So there would be multiple EHR systems. So what if a patient is transferred from hospital 1 to hospital B? How that data can be intelligently be transferred to their systems without much interventions and all that, right? Today, like, I want you to imagine the healthcare system in India today. If for a particular case, if a patient is transferred from hospital 1 to hospital B, what you do, you carry a bunch of files, right? And you go from hospital 1 to hospital 2 and say that, okay, this is what, all the treatment done in a previous hospital. We don't want to do that, right? Do you really need that? No. And let the systems of the two hospital be different, but you can have an intelligent interoperability kind of processing system who can handle this, right? And I can keep talking for like 2 hours on only on this topic, like how can we improve the administrative part in the healthcare system in India. Okay, right from clinical trials till the caregiving. Okay, there is a lot of opportunities for AI in healthcare. Let's move forward. The second pillar, like, another pillar of application is where, you can think that how AI can help. Now this is actually the clinical side of healthcare. Okay, the first is very important, is called as a patient stratification. In a very simple term, is creating cohorts, creating small clusters of the patient, right? Now, today's era, all the, pharmaceutical companies and healthcare, drug discovering company and all that, what they're saying is we are moving towards personalized care. Means what? There will not be a one drug which is applicable for all the people in the world. Rather than, based on some characteristics of the patient, I will create small cohorts of the patient. Like, this is a type 1 patient, this is a type 2 patient, this is type 3 patient. Okay, and different, based on their characteristic, I'll give you, a different combination of a drug. Okay, because a combination of a drug which works for type 1 people may not work for type 2 people. Okay, so if you go to an healthcare domain, you will see that the first application of AI that you will see is clustering. I have a full set of patients data. and based on a particular study, based on a particular disease, based on a particular drug, I want to group those patients. Okay. So in your machine learning theory, you must have learned clustering algorithms. This is what exactly people do here, stratification of the patient. Okay. Then comes other applications of the thing is called as a patient diagnostics. Now this patient diagnostics means, you are actually, you do a lot of tests, right? uh, Blood test and many other biomarker tests that you do it. Now based on that, with the power of AI, you can do some kind of a predictive analysis also, or you can do some causal analysis also, right? If test 1 2 3 4 5, if the results are this, then what is the risk of having something? All this kind of a predictive applications you can do by using an AI. So a lot of hot things which are coming up, and this is all possible because now we are digitizing our data. Okay. Once the data is coming from notes taking, once you do EHR, then this data can be pulled in the flat files, and then they are making it AI ML compatible, so that you can actually run algorithms on the top of it, and you can build some test. And this is not only applicable for structured data, this is not only applicable for flat files. Okay, so it's not only applicable for ML. People are applying a lot of deep learning algorithms also. Okay, so instead of just working on a structured data, you can also think of working on unstructured data. You can start working on X-ray images, you can start working on MRI images, you can start working on CT scan images, you can start working on histopathology images. Okay, and you can run this diagnostic sec. Now if you see that, if you meet an histopathologist who see the histopath images and then gives a decision whether a person is having cancer or not, it takes a lot of time to see those images very carefully. Okay, and that person in an entire day sees so many histopath cases, and there is a manual fatigue. Okay, which may lead to some errors. Okay, but you can completely automate that, or instead of, I'm not saying completely automated, but you can use AI to highlight the regions in an histopath image where humans should be focusing on. Okay, so assist the human expert by using this. And lot of advancements are happening in the imaging applications of AI in a clinical side of it. Okay, and the last category of the clinical applications that you can see is called as a remote monitoring. Okay, remote monitoring, two aspects. If we think about from Indian context, there are so many regions, there are so many villages where doctors, expert doctors, can't go. Okay, so there is an opportunity for you to build handheld devices, which can go do the scans there and do some intelligent processing on the device without having internet connectivity, and then make the diagnostics there itself. Okay, and then take a call where expert doctor is not available, right? On other side, in the developed countries, in the west, there are cases where patients are sitting at their home and the surgery is done, and a lot of devices are connected, and the monitoring is happening from the hospital, because there is a scarcity of expert doctor, right? So they can't go to every patient and see them regularly. Instead of that, you can have an AI system who will monitor the health of the patient, who can monitor so many parameters of the patient, and when something goes wrong, they can actually buzz the doctor on their cell phone, like, this is what happening and all that, right? So these are all the clinical applications which impact the quality of care that you are giving to your patients. It will impact the kind of a prediction or diagnosis that you are getting. So if you see this, this is actually applicable to the life of the patient, right? Either ease of treatment, better test, faster results, accurate results, and maybe less costly results, because very less human intervention is needed, right? So this is all the scope of an AI in clinical side of the applications. If you see the last pillar is kind of an futuristic. Okay, it is called therapeutics or in the research. Okay, So at a one side, you can still use AI for doing drug discovery, clinical trials, finding the right patients who are suitable for my case study, and obviously an R&D. You want to explore something new, invent new drug, invent new test. This is a core data science activity. You collected more images. Now you can think of doing some R&D, saying that I can get a clinical data from here, I can get a imaging data from a scan, I got an histopathology data, and I can build a model, maybe a multimodal model, which sees, because doctor don't see only one kind of a data and take a call, right? So you can think of multimodal kind of a model. So this is all R&D stuff, the core research, where you can either develop new process or you can develop a new test. And it's a very hot area, and companies are investing huge into their R&D, how they can improve the healthcare. Okay, so as I mentioned, applications of AI are divided into three bigger categories: administrative, clinical, and research. And all three are important. And you can choose an area where, which excites you and where you can try to learn more. Now, I want to present, an hypothetical situation in front of you when I'm talking about, advancements of AI. Let's imagine something. Now today you will feel that, Bhushan, what are you talking about? This is, I don't know where these things can happen in in India, in Pune, where we are today and all that. But imagine in near future, probably we will encounter these kind of systems, right? So I'm just trying to give you, or I'm just trying to paint a futuristic picture in front of you, like what is gonna come with us. Okay, so let's understand where AI, uh, where AI can impact uh, our whole journey in healthcare. Okay, so first stage is called as a patient triage, right? A patient reaches out to his provider, so something is wrong. So provider means your care provider, means a doctor. Okay, so patient reaches to your provider, who uses AI to determine his level of risk. Okay, so when something happened, you go to your family physician first. A very friendly doctor may not be always expertise in all domains, right? But you have a emotional connect with that doctor. So because that person may not be expert in that domain, based on the patient condition, based on some few parameters, maybe uh, heart rates, BP, some basic results, some observations, based on all that, that physician actually can use an AI to determine what is the risk here. Should I say to patient like, okay, go back home, take some rest, everything is fine, or it can use an AI to say that no, this patient probably needs an immediate attention from some experts and all that, right? So given patient risk profile is high, he is referred to a specialist. Okay, so then the doctor says that, oh, probably you need to meet a specialist. Now, how do you book an appointment with your doctor today? So you take a call, and don't you think that if you go to any of the OPD in the hospitals, you know you take an appointment, and every patient is processed in a sequential manner, right? Now imagine there is a doctor who is a super specialist, and is conducting an OPD, and there are 8 numbers before you, right? Do you want this person to see these patients in a sequential manner, or you want to actually reschedule, shuffle this list based on the urgency, like, okay, to whom you should see first, right? So behind the scene, the provider's administrative AI tool. Now deliberately I'm using different colors here, right? When I use this green color, means it's a clinical application. It is actually looking your blood reports, it's actually looking your health conditions, and making, AI is making prediction about how much is the risk. Now if risk is high, that should go as a parameter to your scheduling system, right? So behind the scene, The administrative AI tool determines the scheduling that suits the needs of the patient and clinician. Okay, I know right now this particular doctor is available and this is the condition. Immediately schedule an appointment. Or you can think out, or you can think that no, there is no need for this particular to happen. And then you can book an appointment and you can say that okay, you can come after 3 days and whatever it is, right? But this scheduling, which happens in a very manual way today, or there is no way to shuffle this list, or even if it is happening is either the receptionist well and you say, oh no, I am a regular and all that stuff. So this all will go, and this is all will be a data driven. So there will be an AI who will actually shuffle the appointments and the ranking of the OPD schedules and all that, right? Once you got an appointment, once you meet that person, then this is called as a clinical encounter. Now this is the first time you're talking to the specialist, and this specialist shows up to his appointment, and instead of taking notes, the doctor uses speech to text AI to input his notes and ER. Again, this is an administrative application, no action being taken, but instead of doctor writing into the system, the notes are being taken by an AI system. So whatever you are talking to that specialist is being converted into speech into text, entities are being extracted, all the data is going into a database, and this is all done by an AI. Okay, so that doctor can focus on you. When the doctor is talking to you, looking at you, doctor is not worried about taking the notes, because AI can do this administrative work for you. Now the next is data structure. The data from the visit is structured to facilitate the leveraging of the data and other use cases of AI like diagnostics and coding. Okay, the once that notes taking is done, and from that notes you convert that unstructured data into some data structure which is compatible for AI, ML, and all that. So if you have done a machine learning course, there is a first process called as a data analysis and data pre-processing and all that. You don't have to manually do that. AI will convert your raw data into an ML compatible data for you. And then another green point has come. Green means actual clinical applications of AI, right? So diagnostic text. So Jim is that person who is going, I was using you and all that. Let someone like Jim, okay, he goes there and he performs diagnostic test, and it is an AI enabled blood test, and which suggests that patient may have some serious heart condition here, right? So now this AI algorithm is saying that there could be a serious heart condition, and this test is again an AI generated test based on few parameters that you got from a classical pathology test, plus the notes given by the customer. They all can go together into a single model, and that model is an again specialist specific model. So it's a heart related model which is actually predicting that the patient is have a serious heart condition. Based on that, that patient can be transferred to a CT scan or some disease, and patient heart uses an AI to analyze image and suggest the diagnostics, right? So now here today, the CT scan is done, and then it takes how much, like 2 days or 3 days for you to the get report, right? What is happening and all that, right? This all time can be cut down, and you have an AI who can do this diagnostic testing and all that, and immediately will tell you that what has happened with you and all that. Okay, CT scan is just an example. Don't go into literal meaning. Okay, this could be a 2D echo, or this could be angiography, whatever, if it is related to heart. But eventually, you are generating some kind of an images, and those images can be processed by AI to find what is really happening or what needs to be done next. Once that is done, then based on the results of your diagnostic test, there will be a clustering done. Patient stratification means what? Okay, this patient is belong to this category. So AI used to assess the medical history, imaging result, and suggest the form of the treatment that is needed for you. Now again, that I'm talking about, this is not like okay, one fit for all. It's not one fit for all. In the future it would be personalization. So based on your history, based on the current results, AI will tell you what treatment suits you well, what should be the next action done for you. Again, this is a green, this is again a clinical application. And then once this is done, probably you know the next recommendation could be, that person may have to go under a heart surgery and all that stuff, right? Now that heart surgery cannot happen immediately, right? There could be some preparations for that, like at least you need to start some new pills, or you need to stop some old pills, and you need to check your uh, the conditions and all that, right? So that patient asked to go home, but at back home, patient receive communication via gen AI nurse. Now between the time, like, still there are 4 to 5 days remaining for the surgery, and by the time you are talking to a virtual assistant, and this virtual assistant is helping you. So whatever the small queries that you have, can I eat this or not, should I be on a fasting, this is the pill that I regularly take, should I continue to do this or should I not take this, all the typical questions that you have, they call it as a pre-surgery regime. Okay, so surgery is yet to happen, but all preparations of that, who can help you? Virtual assistant can help you for that. I don't have so many doctors to answer all your small queries, right? Virtual assistant can take it over. And then the day comes where the actually surgery happens, and now along with the doctors, we'll see that it's going to be a robotic assisted surgery. Okay, during the surgery, AI, you know provides unprecedented precision for the surgeon, right? Rather than me doing it, the kind of an accuracy that is needed, AI can help me to do actual surgeries. And this is not a future, right? There are so many surgeries that we'll see are robotic uh, assisted surgeries. And when surgery is done, everything is good, then I discuss, you come to a revenue cycle, the billings and all that. And I have already discussed how much time it takes for you to billing the stuff and all that. Again, it can be optimized by using AI, so which will increase, you know not only speed but of the accuracy of the billing and all that. So that Jim paid the bills, and now Jim will go home. And the last step is again a remote monitoring. Now surgery is done, you are back at home, but still you need to take a rest. And in order to avoid any further risk, there would be a remote monitoring. So this remote monitoring is again, it will monitor the biomarker, automatically adjust the precision doses and so many other stuff. And if required, it will call the doctor, right? So what we have seen is patient back in a full health. So this entire process, from the first interaction to your family physician till the surgery, post surgery care and all that, every stage in healthcare, you have applications of AI, right? So that's going to be the impact of AI in healthcare industry. Okay, so I hope you've got this. Now what we can do is, with interest of time, I'll go a little bit faster, and then we'll deep dive into how these applications are built and all that, right? So recent advancement, administrative applications. So as I told you, one of the biggest impact of AI in healthcare industry is a virtual assistant. And again, I have taken this report from some website. You'll see that on y-axis it's a US dollars. So from 2022 to 2032, this much is the business growth. And right now, that, right? Most of the research and inventions are driven by money. Okay, so it is expected, a lot of money into this, so that everybody is working on the virtual assistant. So is it new? In 2022, there were still few companies which were still had virtual assistants, right? So there was a very interesting paper. Do you understand what word that come out of my mouth? And virtual assistant comparison for medication names. Okay, so this is 2019 study. And if you read this paper actually performs comparison between comparison between Amazon Alexa, Google Assistant, Apple Siri. Now in my, this is 2019, before the boom of Gen AI and all that stuff, right? So they actually compared Alexa, Google Assistant and Siri, the general purpose talking systems, how much they understand medical names. Okay, so they repeated measures, they perform ANOVA statistical analysis, and they say Google Assistant achieved the highest comparison accuracy, okay, for both brand name of a medical and a generic medical names. Okay, so 2019 they said that Google Assistant is the best. Okay, now there is a follow-up publication by same folk in 2022, and there they say that now how much is the improvement from 2019 to 2021, how much people have improved in the domain of virtual assistant, again for the name of the same study. Now they say that in 2022 also Google Assistant achieved the highest accuracy score. However, significant increase like 10 to 24% improvement has been seen in Amazon Alexa and Siri, okay, in past 2 years. Looks like everyone is putting a lot of efforts, and you are seeing that even if Google Assistant was on highest, other companies are also showing 10 to 24% of improvement into that. This was year of 2022. What happened in 2023? In 2023, actual virtual assistant applications were published, and by 2023 we were having an LMs also. Okay, so far we were working on language, sequence to sequence models and all that, right? So this is a very nice publication which says that clinical accuracy of large language models and Google search responses on postpartum depression questions. So these women are asking this questions, and they use this and they say that LLM responses for PPD questions based on the clinical accuracy, and what they're saying that a contextually appropriate response that reflect the current medical knowledge. Okay, so amazing paper published, and they say that wow, LLMs are actually able to give the correct answers for these things. Now today is the the age of agentic AI, right? 2023 LLMs were sufficient. Now you go beyond large language model and you are actually going for an agentic workflow. So I don't know how many of you have learned an agentic AI philosophy. Uh, I'll just quickly give you spend some 5 minutes to give you what they are, and then I come to this case. So an AI agent still have large language model, but apart from large language model, it has a memory also to know more about the end users. It has another component called reasoning and planning, which helps to plan your actions and all that. Very importantly is it's not only depend on large language model, it can fetch data from some database, or it can take some live information from internet or some other tools also. Okay, so very importantly is what is difference between a chatbot and agent. The difference between that, AI agents are autonomous. Autonomous means they can take their call on their own. They are not explicitly programmed. Okay, so because they are not explicitly programmed and you are giving autonomy to an AI, we have seen altogether different user experience now. So today if you make a call to any call center, if it is a simple chatbot, you will see that the interactions are very robotic. They will say that if you want to do this, press 1, if you want to do, press 2, and the moment you say something, then it says sorry, I'm not programmed for that. So you get frustrated, you say, boss, I don't want to talk to this robot, switch this call to human, I want to talk human executive, right? But now with agentic workflow, you will see that this is your AI agent, and user can actually speak to it, type to it. Okay, and via different channel, you can talk to Teams, you can talk to Skype, you can talk to WhatsApp, you can use any other devices, and you can use your cell phone, home internet, from your car, so from all the different devices, all different modalities of communication and all different channels, you can reach to this virtual assistant. And this virtual assistant has language understanding, it can understand images, it can perform question answering. Okay, now this assistant, you can extend the capabilities of large language model by connecting to an external data source. It can read research paper, it can read policy documents, and all that stuff. And conversation skills, right? It can book an appointment for you. So agents, they can take an action also, right? So they can book an appointment for you. They can, email to your doctor, by some other tools, and they can talk to other assistants also. So that's how the world is moving. So people don't like to have passive bots, rather than they're looking for an agent who understand what you want and who can perform action, who can take a live data, and you know who may be connected to your smartphones and devices, right? And that's why this growth, is what you are seeing in this. So AI agent has a reasoning loop, it has LLM as a heart, but very importantly, it can connect to an external tools. So the most popular application that you might have learned in Gen AI is called as a RAG. So instead of, you know classical RAG, where user is just reading from some databases and giving you an answer, people will build agentic RAG. So apart from your data sources, you can connect to external tools as well. And because this is an agent, when you pass an query, and if the answer of that query is not in your database, probably an agent can do a Google search or do some search into some medical websites and tell you that I didn't get answer in your document, but this is what particular website is talking about and all that. So these responses will be more human like responses, right? And then from one agent, people build multi-agentic systems. Okay, so you'll see that lot of growth into an agentic AI based virtual assistant in healthcare systems. So the traditional RAG, use when user fires a query, they retrieve your answer from some external data and then use to generate answers for you. Now, from traditional RAG, people will go to advanced RAG. They'll do a lot of query transformation, re-ranking, and filtering. And from advanced RAG, they'll go to agentic RAG, where agent can do the task planning, query transformation, dynamic context management, and maybe taking actions. Instead of just giving you answers to your question, it can go and actually book an appointment. It can actually go and do the payment for your OPD bookings and all that stuff. So this is all about the developments that we are seeing on virtual assistant. So I really like this particular visualization that I got on Microsoft Healthcare website, really showing the whole plethora of opportunities for you, right? So for an end user like you and me, our scope would be like take one channel, one type of an input from a one device, and build this end-to-end system, and it will keep adding and growing over the period of time. So let's move further. Let's see one more administrative application, and that application is about note taking. Okay, so this is your doctor, and doctor will have an access to speech to text, or doctor can write on a paper. So I have seen there are devices. So because some doctors, they still have an habit of writing this, so this could be an electronic pad, or I have seen some application where this is actually a physical paper, and they use some special type of a pen, and within that pen the camera is embedded. So when you write on this special type of a paper, as you are writing on this paper, you see that OCR is been done, and you have a raw text. Okay, so a lot of research opportunities for you in this, and there are already products in the market who are actually giving you some papers to the doctor and dedicated design panes, and then doctor are writing on their paper, so patient can take this paper, but whatever doctor has written will be directly digitally saved here. I have seen such live applications. Okay, it's not futuristic. On other side, speech to text, though, it's like a kind of a small problem for many of the tools now. Then you got the raw text. The moment you got the raw text, then here AI comes into the picture also, like how you are post processing it. So in a machine learning term, this problem is called as an NER, name entity recognition. There are dedicated models for healthcare industry who extract the medical terms from the text, from clinical notes, and then they will put it into this data in a structured format, and then this data can be used further for doing data analysis and all that stuff. Okay, So lot of opportunities here. If you want to do some research, just do some literatures survey on this, and you will find that lot of opportunities in this pipeline. So what it is done, like once the note taking application, this note taking application will put it on cloud, and from cloud it goes to an ELR or EHR system, because these systems are centralized and they grow in a scale. Okay. uh, Again, if you really have interest, like what does blue box done, you can actually visit this Google Cloud blog, and they have, entire system developed. Rather than you to building it from scratch, you can reuse this architecture, and you can actually uh, develop the systems. So this note taking engine will be yours. Rest of all is already developed, and you can reuse that. So next challenge that people see is an, healthcare interoperability. So because every doctor has a different style of writing, you will extract some entities, and because every people are writing their own engine, eventually it should go to a central database, right? So these are the different EHR providers, but you should have an interoperability between those, right? So this EHR and this EHR, right? So that's what I talked. If you change hospitals, their systems will be different. So how smoothly you can convert data from this format to that format. Okay, so the Google come up with an protocol called FHIR, which is called a Fast Healthcare Interoperability Resources Protocol, which will help you to transfer a data in a RESTful protocol manner, and the representation will be in a simple JSON and all that, right? So that you can do. Let's see another application in administrative pillar, and that application is called as a revenue cycle operations, right? So amazing paper, again it is published on McKinsey blog. It's saying that setting the revenue cycle up for success and automation in AI, this is what. And during an intro of this session only, I told you, right, how much time do we waste in the hospital only because your claim is not approved or your bill is not ready and all that, right? So we need an AI to optimize the soft staff time. We want accurate billing, and we need to assess the risk, right? So it says that about 46% of the hospitals in a health system now use AI for their RCM operations. Okay, RCM stand for revenue and cycle operations. Now I don't know whether it considers whole region, but I think it will tell you, like, you know how much is an opportunity for us, right? So you can build systems, and there is a lot of future for that. Revenue cycle operation use cases, within that what you can do is automatic coding and billing, right? So AI driven NLP, this system automatically assign billing codes from clinical documentation, reducing manual efforts. Claims, okay, AI identifies and correct the claim errors and before submission and reduces. So why wait that you will submit a claim and then it get rejected and all, right? You can think of building a system like when you're submitting the claim, there could be an AI system will proactively find, like, here could be an error. Okay, so you can avoid denials. Okay, predictive analysis for denial system, likely denials and their causes. Machine learning models can analyze denial patterns and may suggest you the corrective action at the time when you are filling the bills. Revenue forecasting, accurate revenue forecasting, so it's a typical regression model, forecasting model, like, this will help me for budget planning, resource allocation. AI stimulates financial, so informed decision making, right? So based on a pattern, you'll see that, okay, in this particular unit of my hospital requires more resources, so you can do a resource planning and all that. AI personalizes plans. Understand this, like based on your financial situation, based on your health condition, it can help you to decide which insurance plan you should be taking. If you have a queries about your billing, you can talk to a virtual assistant about, why this bill is so high, is it correctly given, how can I save my bill, and so many questions related to bill. Okay, moving to some, and this is one of the favorite part, that's why I love working in healthcare, because whatever work that you're doing in AI, if you build some very good clinical application, eventually it will help to save lives, right? So whatever work that you are doing, you can save somebody's life. And that's why this is something very close to my heart. And I got an opportunity to work on very exciting uh, clinical applications about predicting cancers and all that. And it's already in production and people are using it. Okay, so the first application is, as I said, is the simplest application in clinical side is patient stratification. Is like categorizing patient into subgroups. So you can consider factors like age, clinical data, genetic mutation, disease stage, and lifestyle. And then you can create clusters of the patients. And once you have a patient clusters ready, you can use those clusters, and then you say drug development, personalized medications, and improved clinical trials, right? Rather than doing one for all, you can actually cluster your patients and have a personalized plans. So clinical applications. Now, if you have interest, okay, on building something, understand this: to build clinical applications, you need humongous data set. Okay, even if you are trying to build any deep learning kind of a model, you need humongous amount of data set. So it's not easy for people like you and me to sit in the college or at home and think of collecting some images and try to build a model. So instead of that, or rather than building from scratch, you can use some foundation models. Foundation models means these are the models who are specialized in that domain. Okay, so what I'm showing you are some of the models which are developed by Google, and those are available on Google Cloud Platform under Vertex AI. Okay, so there is one model called Derm Foundation model. If you're working in dermatology images, you can use this models. What it does is, you give image as an input and pass it to this Derm Foundation model, and what you get is a vector out of it. Okay, so this vector is, you can say that, some representation, some an intelligent representation of what is there in this dermatology image. And on the top of it, once you have a vector, now this is in a structured format, yes or no? On this structure format, what you can do is, on the top of it, you can perform machine learning. Okay, or you can apply a neural network on the top of it and do your classification log like 0 and 1 based on whatever the use case that you have. So the biggest blocker is, because they have already trained this dermatology foundation model or pathology foundation model or x-ray foundation model. There is no need for you now to collect like terabytes of a data. Okay, or hundreds of thousands of images you don't have to collect. Rather than, you can stand on their shoulder and take a longer jump. So if you're thinking to do some research in dermatology, some research in pathology, some research on x-ray, you can consider this as a toolbox, and they will do the most of the heavy lifting for you. That you can use those pre-trained model, perform a feature extraction, and build your own ML on the top of it, and you'll get the best results. Okay, so you can leverage these foundation models. I'll skip this particular portion which goes little bit too deep into like what options that you have and all that, right? One of the thing is, you can use them directly as a tool without doing much, like take somebody else model and do it. Or you can have specialized models in a based on the modality. So this is a multimodal model where you have an chest x-ray and mammogram, and maybe you are predicting a cancer. Or you can have different modality specific extensions, or you can use mixed modality kind of a stuff. So these are some of the technical details of how you will build those models, which I may skip for a moment. So just have a look at this, so how this dermatology app works. So this is how you can imagine of building an application. So all what I'm showing is already available on public domain. It is already published in Nature Medicine, and already showcasing amazing results, right? So this was an application that in a clinical diagnostic that people are using in a dermatology domain. Similarly, you can use it for eye images or retinopathy images. uh, you can use it for predicting lung cancer. So these are already, published work that I'm showing you, that how AI is, detecting lung cancer. Hidden size of anemia. So this is something very exciting, right? So predicting anemia from eye. Now anemia, it's in clinical conditions and all that stuff, right? But a reflection of that disease on eye image, and a correlation has been done with, the signs of anemia from just an eye image. So these kind of in clinical diagnostics you can build. How AI can help breast cancer screening in clinical practices. Again, these papers are published in Nature journal, and you can read these applications. Now let's move towards some of the recent advancements that we see in the research side of it. Okay, now we'll see that yesterday this year's Nobel Prize was announced, and the Nobel Prize of Physics has gone to one of the Googler, who was who built on uh, 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 quantum computing. I just forgot the details of that, but this was the last year's Nobel Prize, and you can see that the Nobel Prize of Physics has gone to Sir Geoffrey Hinton, and for their work in a neural networks. So see this. This is an impact of an AI, right? Nobel Prize of Physics is going for neural networks. Nobel Prize of Chemistry, okay, again, Demis, he is a Googler. Jeffrey Hinton was a ex-Googler, and you'll see that this is for the, using an AI, they built a system to predict the, protein structure. Okay, so Nobel Prize of Physics, Nobel Prize of Chemistry is going to AI. Okay, so AI taking Nobel Prize, this is something news, and this is happening in 2025 also. So that's the trend. So this is a Google DeepMind has open source an AlphaFold. So those AlphaFold has already been used by more than 2 million researchers to, use their advanced clinical work, from enzyme design to drug discovery. So DeepMind has open sourced this. You can use it and start building your own research in a biology by using an AI. So, AI enabled drug discovery is another research area. It's a process of identifying and evaluating molecules. And we are seeing that on an average, naturalists take 10 to 15 years to develop a new drug, right? And this cost almost 2.5 billion dollars. But with help of an UI, this achievement was accomplished in just 30 months. So when there was no AI, people used to take 10 to 15 years, and with the help of an AI, in 30 months, people are developing. And in February 20th, FDA entered their inaugural distinction of AI generated. Now, FDA also approves AI generated drugs. So this is best time to work in this area, where you can use AI and you can invent a drug. So this all find exciting, right? We divided applications of healthcare into uh, three categories. Category one, uh, we discussed about, was more about operational sides of it. Category two was on clinical side of it, and category three was more on uh, research side of it, right? So this all looks good, but what are the challenges, and what are the future scope? This going to be a good thing to discuss at this point. So these are the classical challenges, when you work, on AI side of it. And very importantly is the data privacy and security, right? So the way you get any kind of a data, getting an healthcare data is really a problem. Okay, so unless you are not having a tie up with some research, clinical research institutes and all that, if you want to build something, getting a data is very challenge. Okay, and that's why, because of a data, now there are a lot, these rules are so strict, so it's very hard to get hold on healthcare data. So, and you know that if there is no data, there is no AI, right? So this is one of the blocker that we are seeing. Second is algorithm bias and fairness. As I said, uh, because getting the data is difficult, people are still building AI models, but those models are limited. So this is, this is country one and this is country two, probably not much advanced country, not much digitization happened. So this is country one, lot of digitization, interoperability and all that, right? So they get the data and they build the model, right? But what you get is, the data for the same country, same people, same race and all that stuff, right? And now people try to use this algorithm on these countries, so they won't work, right? So those are the algorithmic biases and the fairness, and that is uh, one of the biggest challenge in healthcare. Second is an explainability and trust. As I said, lot of these deep learning models are called as a black box models, right? And then people don't trust it. Like, if this is a test and this is an AI generated test, and you got your data in, and then if AI says that this person has a particular disease, right? How can you trust it? you know so even doctors don't trust AI if it is a black box, right? So there is an always trade off. So if you want to do some research on this, this is a trade off that we normally discuss. What is the trade off? On y axis you have accuracy, and on an x-axis you have explainability or explainability or interpretability, right? So people say that this is the current situation. You can't get both. Either you will get high accuracy, like you can use deep neural networks and all that stuff, so accuracy will be high, but you will not be able to explain your decision. It will be a black box. Or you can use very simplistic algorithm like logistic regression to make a prediction. So it is inherently explainable model, but it is a linear classifier. So the on accuracy front, probably you will struggle. So if you want a research problem for this discussion, this is a research problem for you. Like what I want is, I want a highly accurate but explainable model, right? How can you do it? Probably it deserves a PhD on that. Okay. So explainability and trust is a biggest challenge. And then regulatory approvals and standardization, because it's an AI, people are still wanted to make it doubly assured. Like, have you really taken a good samples? Are your tests fair? Are your results correct? And it takes time, to approve your AI system. Okay. Over the period of time, I believe this would be faster, but currently it's a challenge. So security, data breaches, AI system require massive amount of patient data to function effectively. This data includes not only medical histories but also genetic information, lifestyle data, social factors. Okay. Now, what if this information goes out? It's like gone, right? You know everything about it, and the bad actors can actually use this information to threat you, to blackmail you and all that stuff, right? So data breaches from hospitals is a biggest concern. AI system themselves can be vulnerable to attacks. Not only the attack on a data, there could be an attack on AI system also. Attack on AI system means, I'm a bad actor, I'll actually go and fool your AI system by poisoning the weights of your model or poisoning into a training data on which you are trained. Okay, so it's called, hackers can manipulate data fed to AI algorithms, which leads to incorrect diagnostics. Okay, ransomware and data encryption risk. So this is I don't know how many of you know it, right? Few years back there was a cyber attack on AIMS, right? And they ask for ransomware, like, we have hacked all your patient data, so you give us that much amount of money, otherwise we will leak that data and all that, right? So that's why, healthcare applications are need to be very secure. Privacy and bias, data anonymization challenge. AI system are, that research has shown that anonymized data can be re-identified. There is an amazing use case. I don't know if you have seen that. That use case is called Netflix $1 million challenge. So Netflix collected their user data and they did an anonymization, and there was a competition launch which say that if you build a recommendation system which work better than our matlab Netflix recommendation system by more than 10%, we will give you $1 million. Okay, they say that will give you $1 million. Okay, so people took this data, and there is an open data called IMDb. Now in this IMDb data set, people have their names and all that data. It's an open data. So what people did is they use this IMDb data and do some stuff, and from this Netflix data they actually reveal the name of the people and all other information, right? So just data anonymization is not enough. Okay, second is about content and data ownership. So what happened is, rises about patient consent, right? You People are taking data from patients and they are building an AI model. Okay, once AI model is built, we don't need this, right? So now people will sell this AI model to make further prediction and all that, right? But what about the patients who donated their data? So who owns the data? Like if they owns the data, they may claim ownership on your AI models also. So this is again a culture and a bias in a system. I already discussed. Like if the data is not inclusive, there would be a biases in your data. Regulatory apply HIPAA challenges, GDPR, AI specific guidelines. In India also there is a new law which is passed in the parliament but not yet started. The implementation is called as a DPDP. This is called as a DPDT law, data protection and data privacy law in India, which is approved in the parliament. Now once this is applied, it will be even difficult for us to build AI applications and all that. So some of the highlighting innovation. So if you want to really try something new, and especially into a medical domain, there is a dedicated Gemini model in the medical field. It's called as a Med Gemini. Okay, so it has advanced reasoning, multimodal understanding, long context processing, self training, fine tuning, chain of reasoning. And you'll see that on an x-axis, there are so many other models. This was a MedPalm. Again, it was a Google's model. It was a MedPalm 2. There was a GPT-4, and this is a Med Gemini. Okay, it shows the amazing results on uh, medical question answer data sets. So try to use this model as a starting point of your research, and you can think of developing something on the top of this. Accelerated development of AI. So once you have a Med Gemini, right, this is like in one model. No matter what medical modality you have, you just need one model. That's how the world is moving. So just use Med Gemini. Let it be the CT image, dermatology image, DNA data, uh, MRI, histopathology data, or eye images or clinical notes. Everything can go to a single model. Let your data be 2D, 3D, or gene sequence, and you can build classification, VQO, 2D report, 3D report, everything. Okay, that's how the development is happening. And there is a very interesting area where you can think of doing some kind of an research. Is called as a federated learning. Okay, this is called as a privacy preventing AI. Okay, so difference is what? See, people don't share the data, right? So the concept here is, okay, you don't share your data, model will come to you. Means what? There is a central agency where AI folks are sitting, and this is a central lab where you are building a new AI model. This is an hospital one. This is hospital one. This is hospital two, and this is hospital three. Okay. Now, what is happening is these hospitals, they are saying that we will not share our patients' data because of some like we are not allowed to share a data. So what people say is it's okay if you're not able to share a data, I will send a model to you. Okay, you don't, if you are not able to share a data, don't worry, you can share a model to me. Okay, so instead of data coming to a one central page, this is a M is a model. So this same model will go to different hospitals on their premises. Training will happen on their premises. So you will have a new version of a model which is coming, which will be M1 or M plus delta W1. Delta W1 stands for change of the weights of your neural net, right? Similarly, this M plus delta W1, you will get M plus delta W2, and then you had the base version of a model, plus you have a collection of change of a weights, delta W1 plus delta W2 and plus delta W3. And what you will do is you will use some intelligent logic to take help of this. Maybe you can do some kind of an averaging or intelligent processing on the top of it, and then you will come up with a new version of a model that is an M dash or maybe M2 version of a model. And this M2 will be given to all the participants in a federator journey. So what is an advantage of this hospital H1? Hospital H1 had a data of only some people. Okay, H1 contributed in a federated learning by sharing only delta W1. In return, they got M2. In return, they got M2, and this M2 has a learnings from W2 also and W3 also. So in a way, you got a new version of a model, and in a way, you trained ML model on a data to which you are not having access to also. So this is amazing concept called federated learning. Uh, there are some challenges. Okay, I can do this, but federated learning with large language model, it's something you know is what uh, people demand. I don't know whether it is possible or not, or what challenges will come, but this is certainly being a hot area that people are researching. Okay, so you can think of exploring that. This is a case study of brain tumor segmentation on a brats. It's a very popular data set. I think London School of Medicine and NVIDIA together performed this study, and they actually train a federated model. Federated large language model, as I said, that integration of large language model and federated learning is a hot area, okay, where the research is going on, and you can definitely double click on that side. So what are the challenges of federated learning? Combination of black box LLMs and federated learning. So because LLMs, they don't, sharing the weights of LLM is so difficult that if you don't know, how can you do that, right? So how can I effectively combine black box LLM with federated learning? And knowledge destination is all that. So there are some fundamental limitations, because these large language models, you don't have access to weights. You just call them via an API. So that's a problem. Okay. uh, by raise of an AI agents, you may see that because nobody has a time to read so many papers and all that, this agentic AI can read so many papers and come up with some new invention. And rather than just understanding the paper, you can use agents to write a new paper also, and you may come up with some new discoveries also, which we never even thought. So it's a very crazy concept. Okay. And I believe that's it for the today's session. Maybe I'll end my session on this meme, like, this might hurt a little, and in case saying that AI gonna replace you, and doctor still feel that it's very difficult to replace them. So that's it from my side. I hope you like the discussion, and I will reserve some time to answer the queries. Thank you so much. Any questions?
Yes, participant, if you are having any question, please unmute yourself and ask the questions.
Okay, so if there are no questions, probably
Yes, I think
I
so.
can give you 10
Yes,
minutes.
sir.
Thank you.
Yes, sir. I would like to extend my heartfelt thanks to Dr. um, Bhushan Garware, sir, for delivering such an insightful session and inspiring session. Thank you so much, sir, for sharing your valuable knowledge and experiences with us. Thank you, sir.
Thank you.
Thank you.
Thanks.
Yes, participant, fill the feedback form. Yes, all of you fill the feedback form. I have shared a link.